So last time we had started this section, we were looking at affine and projective planes, and we were talking a little bit about how it's really easy to take a projective plane, remove one point, and you have an affine plane. Going the other direction takes a lot more work, and we were actually going through the process of doing that. So let me just remind you what each of those planes are. I know they're in your notes, but an affine plane is a model of incidence geometry satisfying the Euclidean parallel postulate. Okay, so through every point that's not on a particular line, there's one and only one line parallel to the line in question. That's the Euclidean parallel postulate in a nutshell. And we've given some examples. A projective plane is a model of incidence geometry having the property that any two lines meet, and every line has at least three distinct points on it. And the every two lines meet business is the part that feels a little bit funny, because that's not how we think about geometry typically, right? We're used to working in Euclidean geometry. I'm going to give you an example of, it was a couple class periods ago, about geometry in a sphere, and about how if we do great circles as our lines, in fact, every two great circles does in fact meet. So where we were this time is we were, and I'm going to give you an example, spot it later, is we were completing an affine plane to create a projective completion. So to create a projective plane. And this is where we had gotten to. So I think this should be in everyone's notes. Does that sound right? Fantastic. All right, so these are the four different cases. These cases came about because of the way we defined our equivalence relation. This relation, L is equivalent to M, means either they're equal, right? L is equal to M, it's the same line, or they're parallel lines. So there's four options. The first one being that they're actually equal to one another. L is equal to M and M is equal to N. And then the others are versions where we mix them up, case 2 and case 3, where one of them is equal, the other one's parallel. And then in case 4 is where we have two sets of parallel lines. And we want to actually be able to show in each case the transitive property that L is equivalent to or in the same equivalence class as N. Okay? And we have to prove them. These are our four cases to prove. The first three prove very quickly, and the last one takes a little bit more work. So showing that L is equal to M and M is equal to N is very quick, because if they're equal to each other by the equivalence relation of equality, L is actually equal to M as well. Right? We've changed into something that we know a fact about, equivalence of equality, right? And that means then L is equivalent to N, because they are in fact equal in that case.
Did you mean to write L is equal to N?
Yes, I did. Thank you so much. Just half of an M, right? Okay. The next one, we have L is equal to M, and M is parallel to N. So if this happens, then what's going to happen between L and N? If L is equal to M and M is parallel to N, what can you tell me about L and N? They are parallel, you bet, because L and M are the same thing. So if then L and N are parallel, we can conclude that L is in the same equivalence class to N, because that was one of the two ways that they could be in equivalence class together. Case 3 is exactly the same thing, right? If L is parallel to M and M is equal to N, then L is parallel to N, right? So I told you those three were going to come really easily. The last one's more difficult. I don't have equality, so I can't just replace one like a substitution or something like that with the other one like I did on cases 2 and 3. I do have parallel situations. So what we're going to do is we're going to have to work a little bit on this one. So there's two possibilities. Let me say over here, just write this down. We have to either show that L is equal to N. That's one way that they could be in the equivalence class. Or we have to show that L is parallel to N. So if we could show either of those things happen, or that by a very fact that there's two possibilities that they're forced one of those two to happen, then they'll be in the same equivalence class. So if, we're going to start out with this, so if L is equal to N, then the equivalence class will automatically happen. And that's possible, right? I mean, L and N could have something in common. They would both be parallel to M in that case, and we'd be good to go. So that is a legit possibility. We are actually talking about L and N being the same line. So we're going to assume the opposite. We're going to assume if L is not equal, I don't know why I wrote it twice, is not equal to N, what happens? So if L is not equal to N, and they meet, because that would be the opposite of being parallel, right? So contradiction is what we're going to be looking for. And L and M intersect or meet or incident with each other, whatever language you want to use. So if they intersect, what can you say? What does it mean to intersect? It means they're not parallel, but what would it actually mean if two lines intersected?
They have a point in common.
You got it. Good job, Demetrius. They have a point in common. So intersect at P. We'll call that point P that they intersect. Then there exist two lines, both through P, right? L and M have P in common, both through P and both parallel to M. And what's wrong with that? Yeah, I can only have one, right? This is my problem. So this is a contradiction. This contradicts. This is a symbol I told you before was contradicts. It's really two arrows pointing at each other, but I never draw it that way. I just draw it with an X through the line. This is a contradiction to the Euclidean parallel postulate. Thus, L would have to be parallel to N. And then L is equivalent or in the same equivalence class as N. So this relation is in fact transitive. There's one more item to verify. Did everybody get that written down? I'm sorry, I moved kind of quickly. And that's symmetric. One more equivalence relation has to be satisfied for it to be an equivalence relation that's symmetric. L is similar to M implies that M is, not similar to, L is equivalent to M implies that M is equivalent to L. And that should make sense, right? So if we did a real quick proof of that, there's two options, right? If L is equal to M, M is equal to L, so that one's cool. The other possibility is L is parallel to M, M is parallel to L. So either of the possibilities that exist give us this almost for free. So now we're going to actually define what I keep talking about as equivalence classes, is all of the lines that are either parallel or equal to M. So this equivalence class is going to be the equivalence class 0. I'm sorry, that's supposed to say an L. Does that say? I don't know why that says that. That's supposed to say L. My bad. Typos happen, right? The equivalence class L is all lines M, basically, that are parallel to L. And we're going to call this equivalence class a point at infinity. We're still in the process of creating something. So we've created, in essence, a new point. And the new point is called a point at infinity. And what it is it's every line parallel or equal, but the parallel is the important part, parallel to line L. right, so we're going to define a new plane, A star. A was our affine plane. Remember, affine planes had the Euclidean parallel postulate. That's actually why we were able to prove the transitive part at the very end on case 4, because we were working with the Euclidean parallel postulate. So we've got this affine plane, and we're creating a new plane, A star. The points of A star are points of A. Okay, so all the things that we had before, ordinary points, and points at infinity. Those are our points. So anytime we define, we're working with incidence axioms, we talk about points, we talk about lines, we talk about incidence, right? So this is our situation of what are our points. Our points are the original points we had plus these new points that we've created. Incidence of the ordinary points is inherited from A. In other words, if the two points were on a line in A, they're on a line in A star as well. Each point at infinity lies on the line contained in the equivalence class. So this is how we're defining incidence. What's the last thing I need to define or I need to talk about? Lines, you bet. The lines of A star are the lines of A plus one more line called L infinity. That's a subscript infinity on that L. It's called the line at infinity, and it contains all the points at infinity. A star is called the projective completion of A. So what we did is we took everything that was parallel and we said if they're parallel, we're going to say that they meet at this new point. So all the lines parallel are going to meet at a specific point. And when I include all those points, it means now that I have no parallel lines. That's what it means. Because I just told you, if they're parallel, I'm giving them a point at which they meet. One way to kind of think about this, visually speaking, is imagine railroad tracks. If you're standing on railroad tracks, you have to stand on them for this to work. And think about what happens with perspective. You look down the railroad tracks and you know they're parallel, right? I mean, like, otherwise it wouldn't work for the train. You get that. But if you look in the distance far enough, what does it look like happens to those railroad tracks? Yeah, visually, what we see from our perspective is it looks like they meet. That's a point at infinity. Okay? So that's a picture in your mind of how this is sort of working. A star is a projective plane. It satisfies incidence axioms 1, 2, and 3. But it doesn't have the Euclidean parallel postulate. It has the elliptical parallel postulate. Okay, I want to show you a picture of what this would look like with one of our incidence geometries that had the Euclidean parallel postulate, what it would look like visually if we completed it. So I'll wait until everybody's done writing, but then I'm going to draw some pictures. Okay. Good? Okay, Kennedy? Okay. Is everybody else? I think I was watching. All right, projective completion of the real affine plane. Oh, I missed one. That's why I'm missing my slide. Okay, let me do this. Let me add it at the end. Hold tight. We'll do it here. Okay, what we're going to do is we're going to do an example of your 4-point geometry. Do you remember what the 4-point geometry's visual model looked like? Yeah? Good. All right, I'm going to draw it in here too. So this is the projective plane. Projective completion. I can't even read my writing right now. Projective completion of 4-point geometry. That's our example we're going to first look at. And it started out looking something akin to a rectangle, right? And then we had A, B, C, and D. And then, did I draw an AD next? Yeah? Like this. And then we had BC drawn around like this. More or less anyway, right? Okay. So what does it look like to complete this? Well, it means that for every 2 points, for every point and line that does not contain that point, we need another point. So let's take a line. Somebody pick a line for me. BD. All right, so if I take line BD, tell me a point that's not on line BD. A. So if I have line BD and I have a point not on it, A, then what I want to do is I want to somehow connect that together with another point. All right? So we're going to do that for all of our points at once. I'm going to move my picture down just a little bit. And we're going to do that by adding additional points. So this is actually going to be point E at the top. I'm going to be putting point G in the middle. I'm going to put point F over here. We're going to draw in some extra lines, and I'll change the color just so that you can see that they're different than the ones I had before. Let's go blue. All right, so we're going to draw a line from C through G to B.
How do you know how many points to put?
I'll show you in a minute. Yeah. Let me draw them all in, and then we'll talk about that. So I have from A to, oh, I didn't want to do that. A through E to B, like so. A through F to C. And then I'm going to draw a couple in. I want to draw them in dotted just because I don't want you to think that there's actually an intersection that's not there. There's a line right here between F and G, and then there's a line between E and G. They're dotted. Kind of doesn't come through very well. They almost look like spots though on your screen. So what I'd like for us to do, and I think this will answer your question, Shana, is I'd like for us to label what our lines are now. Okay, so I mean I've included 3 extra points. Those 3 extra points will take care of having all of our lines actually crossing now. So we're going to write down some of our lines. So let me write down one of them. I previously had a line AB. Can you tell what other point is on line AB now? It doesn't draw very well. I don't know that you can. ABF is one of them. We have another line, C, D, F. I will have a better picture of this in a minute to draw for you. A, C, E, B, D, E, A, D, G, B, C, G. There's one more. E, F, G. All right. The easiest one to talk about is EFG, so did I write something down wrong?
ACE,
ACE? Yes?
always down.
You might be thinking of it as EAC. I'm just including them with commas between them. Yeah, just hold tight for a second, Felipe. Let me do EFG first. E, F, and G are points at infinity, correct? They're the ones I added in. They didn't exist before. So we said that that was going to be a line at infinity. So this is a new line that was added to our affine plane. All right, so that's the easiest one to talk about, is the one that we just flat out added. Now let's go back and see if we can figure out where all the other ones came from. Let's start with ABF because it's first. Line AB, right here, had points, it had lines that were not parallel to it. What line is not parallel from our original picture to line AB? CD was not parallel, correct? Or I'm sorry, was parallel. So there's CD. And what we have done is we have added an additional point F. You see it over there on the left? And it's now on this line. There's two lines there. They don't look like lines because they're not straight. I get that. But the point F has actually been created so that line AB and line CD are no longer parallel. Those are now two lines that intersect, and they intersect at point F. So point F has that feature for us. Let's take another line. How about I use, we'll just go with the second one, CDF. So line CD was an original line. Well, I already did that one, CDF and BDF. I'm sorry. So we need the next one underneath. That's what I meant to do. ACE. So AC, this is the one that you had mentioned, Felipe. What line of my original affine plane in 4-point geometry was parallel to AC? It was BD. These two lines are parallel. They did not have anything in common to begin with. So what we've done is we've created point E up here, and we've said that E is going to be both on line AC and E is going to be on line B, on line BD, yeah. And we do the same thing with point G. So we originally had line AD. AD is right here. And the line that didn't look like a line that was parallel to AD is actually BC, right? And we've created point G. We've created point G to lie on AD. That one looks pretty good. Like I saw that. I just stuck it right there in the middle, so that was nice. But it also lies on line BC if we continue in this direction or the other direction. It doesn't really matter which one. This is just a model of it anyway. Now, if I redraw this in a easier way, let me show you what else it could look like visually. You'll like it better, I promise. So draw a triangle. And I want you to put point A is going to be right here. B is here. And we're going to put a point C in the middle. F is on the bottom. D is on the top. E is on the right. Kind of looks like a midpoint. Doesn't need to be, but visually speaking, it'll work if it's there. We've got G on the left. We're going to draw in a few more lines. I want to draw a line in. Oh, I didn't draw that very well. I'm just going to move C down just a little bit so it'll line up a little bit easier for my picture. Where is B? Oh, I'm sorry. It was supposed to be on the bottom. I got carried away looking for C. B is on the bottom left, or bottom right. Okay, ACE is a line. DCF is a line. And BCG, I'm sorry, yeah, BCG is a line. So how many lines do I currently have marked on my screen? There are 6. How many am I supposed to have? with the completion, like if I compared it to the picture above, how many did it have? It had 7. And now I've got 6 of them drawn in, and they are the same 6. I'm missing one. Can you figure out which one I'm missing? What points currently from that listing above, when I listed my lines, is missing? The point at infinity is missing, you're right. And so what I can do is I can actually draw the point at infinity in, like this. Well, the line at infinity actually is what we have, right? That's my line at infinity. And interestingly enough, this is actually another geometric figure. It has a name. It's attributed to a particular mathematician. His name is Fano. So this is Fano's plane. Or the Fano plane, sometimes called too, but I'll call it that way. That's how your book's showing it, Fano plane. So the Fano plane has some very interesting properties, but it's the projective completion of 4-point geometry is what it actually is. Okay, I want to show you another way to visualize what we're doing. I talked about my railroad tracks. We did a specific example for the 4-point geometry. How far back I messed this up. We did that. So here's where we were. The projective completion of the real affine plane, taking the Euclidean plane. All parallel lines meet at a point in infinity. The points at infinity form a line at infinity. And I want to show you one way to visualize this, another way to visualize this. And I'll draw you a picture. I can't remember if it's on this screen or on the next screen. I'll have space. I think this screen. One way to visualize this is to picture the Euclidean plane as a plane tangent to a sphere S at its north pole N. So we're going to just see how bad I can draw today. So draw yourself, that wasn't what I wanted. Try again. Draw yourself a sphere. I'm okay with that, I think. Our sphere, we're going to say, has center O. It has a north pole N. And we have, our sphere's name is S. I think I've labeled that at S. Okay, I think that's what I've got so far. And we're going to draw a plane tangent at point N. All right, so imagine a piece of paper sitting on top of a ball. Okay, so there's my piece of paper, here's my plane, and it's touching at point N. The plane is called plane T. And we have points inside, I'm going to talk about them in a minute, points inside of our plane that we're going to call point P. Okay, so we've got a piece of paper, so to speak, sitting on top of a sphere, top of a ball, and there are points inside of our plane. And our plane is the Euclidean plane, so we have to realize that this continues on forever, right? I mean, it doesn't end, though I've drawn it like it does, because I don't have another way to draw it, really. But this continues in both directions, both directions, left, right, up, and down, so to speak, forever. O is the center of the sphere. And we have points P of T that we can join to sphere O. I'll draw it in a minute. We're going to join them to that sphere by a Euclidean line that will intersect the northern hemisphere of the sphere at a unique point P prime. Let everybody write this down because I'm going to have to go back to the previous screen anyway to draw the picture. Okay, so what we're going to do is we're going to connect our point P to the center of the sphere O with a line. Okay? If you want to go back to your picture, wherever you put point P in that plane above, connect it to point O with a line or line segment. If you want to draw just a line segment, it makes it a little easier. I'll be back on the screen in a minute. So visually, we're connecting these points like this. And there will be a location where that cuts through the sphere. And that location is the projected point P prime. Okay? So over here, it looks to me like it's, I'll use a different color to make it easier. Right here, this would be point P prime. Okay? And we can do that with every point, right? Every point in my plane is going to cross through the sphere exactly in one location when I connect it back to the center of the circle or the sphere. And the further out we go, the further down it's going to be on that top hemisphere, right? And the closer that we are to the North Pole, the closer it's going to be to the North Pole on the hemisphere. Now, the point N itself is going to just be at N because it's tangent to the circle. So N is no different than its projection. Every other point would be, though. Okay, did you get everything on that slide written down okay, Felipe? Okay. All right, so keeping going with this information, this gives a one-to-one correspondence between the points P of T, so the points in the plane, and the points P prime of the northern hemisphere of S. Right? There's a one-to-one correspondence here. But it only projects to the northern hemisphere, right? There's no way that I could get to the southern hemisphere because I'm going to hit the northern hemisphere first with this line. Okay. It's on another slide. Is everybody good? All right. So let's talk about what happens to lines then. Well, similarly, any line in our plane, if we join the line to the circle O, it will create a plane. Right? Imagine you've got something two-dimensional. Right? It's one-dimensional in the plane, and then you join it to something that's in the sphere, so you're going to have a two-dimensional object, a plane. And this plane will actually cut out a great circle. We've talked about those on the sphere. And similar with the hemisphere, it would be a great semicircle on the northern hemisphere. So a line in the plane becomes a great circle on the sphere. And again, this is a one-to-one correspondence then between the lines of the plane and the great semicircles of the sphere, of the northern hemisphere. And this will preserve incidence. I think we just have one more line on this, or one more slide on this example, and then we're going to take a break, okay? Okay, is everybody good for me to switch slides? Okay. So what happens if we have parallel lines? Because we had parallel lines in the Euclidean plane that's tangent to the top on point N. So if L and M are parallel in the plane T, then the corresponding planes through O will meet in a line lying in the plane of the equation, which cuts out a pair of antipodal points on the equator. So antipodal, if that's a word that you haven't come across before, would be like the North Pole and the South Pole. They're on exact opposite sides of the sphere, okay? Exact opposite sides of a great circle. And they would be on the equator. Thus, we can visualize the points at infinity as the antipodal points of the equator sort of glued together. The line at infinity is the equator itself. So I'm going to do my best to draw a picture of this while you guys are writing that down. So that should sort of look like a hemisphere now. That's my goal. And this that I'm highlighting in yellow is the equator, and it would be our line at infinity. All right, I believe this is the last concept that we're going to do in this section. This is called duality. So this is the duality of the projective plane. So we're going to let P be a projective plane. The dual is P star, and it defines points of P as lines of P star and lines of P as points of P star. So we're switching the definition of what lines and points are in a projective plane. Lines are now points, and points are now lines. And when we do this, we actually get another projective plane. So the dual is called P star of the projective plane P, and P star would actually be another projective plane. Remember, projective planes means that we have the incidence axioms, that we have the elliptic parallel postulate, and every line has 3 points on it. Those are the conditions. We're going to take a look at a projective plane we looked at already today. Do you remember what new projective plane we looked at? I drew a picture that looked like a big old triangle. Phanoplane. Yep. Okay, so start with a picture of phanoplane. I'm not going to use the letters I used before. I'm just going to call them P1, P2, so forth. So this is P1 at the top. Okay, that didn't work at all. P1, P2, P3, P4, P5, P6. Yeah, it would have been better if I'd have made it centered. I'm going to try that again. Let me just move this one at the bottom over a little bit. That's better. And it's P7 in the middle. And then I'm going to label our lines. So our lines are they connect 3 at a time. I'm missing one of them still, but our line on the outside here will be L1. In fact, you know what? Let me use a different color just so that I can reference them maybe a little bit differently. Here's L1 on the outside. So this goes from P1 to P2, P3. Keep it like I do have it here. L2 is through the middle, and L3 is on the left. L4 moving sort of counterclockwise, and then L5 on the bottom. L6 It's this line over here. And then you notice I'm missing a line, right? What line am I missing? Yeah, the infinity line, the one that went through here. And that infinity line is line L7. All right, so if I take this image and I switch my lines and my points, I actually will get a very similar image to this one. So I'm just going to draw the same triangle again. And literally what I'm going to do is everywhere it says P, it's going to say L. And everywhere it says L, it's going to say P, because that's what we're supposed to be doing, is switching lines and points, right? So, probably be easier to do this if I just draw the lines to begin with. So this is L1 at the top, L2, L3, L4, L5, and L6, and it's referring to the what appear to be points, right? And that's L7 in the middle. And then our lines, which were written now as points, are P1, P2, P3, P4, P5, P6, and the one that's missing, the infinity one, P7. All right, we have one note about this that's important. A projective plane and its dual are not always isomorphic. And in case you haven't heard or used the word isomorphic before, or maybe in a while, it means similar in form. They are not always similar in form. The principle of duality says the following: if a statement has been proved to hold in all projective planes, then the dual statement obtained by interchanging point and line automatically holds as well, and no further proof is required, because the dual is itself a projective plane. So whatever you can say about points in a projective plane, you can say about lines in the dual space, and vice versa. I will put this slide back up in a moment. I know some of you write faster than others, so just hold tight. I have a handout that I'm going to give you. It's got a couple of problems on it, but it was easier to do it in a handout form, and it will be due Tuesday as well.